Good morning, friends. Today we will discuss about Numpy. This is a very basic introductory course on Numpy, and I would be using Python 3.10, Numpy this version, and Jupyter Notebook to run all the commands and demonstrate all those Numpy features. For a table of contents, first of all, we'll have a very basic introduction on Numpy and what is the use case in data science community. Then we'll go with the installation and setup. We'll install Jupyter Notebook and all else NumPy, etc. in our own virtual environment. Then we will go through the array fundamentals. And finally, in the fourth point is the most important, where we will open our Jupyter Notebook and go through all the commands and all the methods which are available in NumPy. NumPy is the fundamental package for scientific computing in Python. All the other modules, for example, we have got pandas, series, scikit-learn, scipy. For all of these, NumPy is the basics, is the fundamental package for all these higher level libraries. So NumPy is actually a multidimensional array data structure. So it contains of like 1D array, 2D array, or like any type of n-dimensional, and it's always called as ndarray in terms of if you go more technical. And the most important feature is that all the elements inside these arrays are homogeneous. What it means is should be all of like int type or float. So it cannot be of like multiple types as it's supported in Python lists. It should be always in the same type for all the elements for the array. And what makes it different than the Python sequences is it is all the functions, all the methods that we can apply on these ND arrays, they are performed by the precompiled C code. So we already have got all those like methods which are compiled written in C, and it's already precompiled. So it means that it makes it very fast because C is like the very close to the machine language. So that's why all those like precompiled code, all the functions that we operate on these ND arrays are very fast. So let's go through the basic differences between NumPy arrays and the standard Python sequences like list or set. So NumPy arrays have a fixed size at creation. This is very important attribute of it. As we know that Python lists, it can grow dynamically. We can always append or extend it. But for NumPy arrays, the size is always fixed at the time of creation. Just like in Java, when we create an array, it's always fixed size. Changing the size of an ND array will create a new array and delete the original, which means that it's always immutable. Whenever you try to mutate the size, it will always create a new ND array. So this property is very important, which makes it fast, and we'll discuss about it later. The second property is that the elements in the NumPy array are all required to be of the same data type. As we already discussed, that these are all homogeneous. It should be always of the same data type. It should be always of int or float But as we know that in Python lists, we can add any type of type. I mean, we can add an int, float, string, whatever in the Python list. But for ND arrays, it should be always of the same data type. Also, I mean, because of all these like features, it makes it very efficient for operating on large number of data. When you're talking about big data, and when we are talking about like the data in GBs or terabytes and all, in that cases, Python list would be very slower, and we can actually measure the performance. It's like far better than the standard Python sequence. NumPy would be performing very fast as opposed to Python sequences. And because of its very high performance, all the other modules, there are a lot of like Python-based packages which are using NumPy arrays in the background. What they do is that they typically support Python sequence input, but they convert each input to NumPy arrays so that the processing is very fast, and then often output as NumPy arrays. So the input can be Python sequence, but for higher performance, they convert it into NumPy arrays and then process it very fast using the precompiled C code and all the methods which are available on these NumPy arrays, and they often output the NumPy arrays. So we're talking about all those other libraries and modules which are available in Python. So why is NumPy fast? Let's go into more details about it. So there are two properties which make it fast. First is that it's fixed size at the time of creation, and the second is that it's all of the same data type. So if we talk about this, say, suppose this is a 1D array which is having like 4 elements. We already know that it's all of int type. So if int is like of say 4 bytes or 8 bytes, so Suppose if I know if I'm a compiler and if I know the address, the starting address of this. Suppose in the memory, this address starts at say 100. So I already know where would be the second element, the third element, and the fourth element, because I can just use 100 plus say 4 bytes would be the memory 100 plus 4 bytes would be the second element. Memory 100 plus 8 bytes would be the third element, like this. That's why the compiler is very, very fast to fetch an element, or which is always in the O1 time, because once the compiler or the interpreter, it knows the starting point, the starting memory address of the first element, it can already know in the O1 time for the rest of the elements. Access is very, very fast. And the second thing is, because it also knows that it's always of the same type, it should be int or float or whatever. That's why the size is already known. That because each of the int or float, it will take 4 bytes or 8 bytes according to the architecture, but the size is always known. In case of Python lists, because it's dynamic, it can be growing dynamically. Every time the interpreter has to check first of all the type, what is the type of the element which is stored at that particular array element, and also it has to just it can never judge the size of this Python list, because it's dynamic. The size can change. So every time whenever you're doing a for loop in the Python list, which is a very common way to iterate through to any Python sequence, so it will go through each of the element. It has to interpret what is the type of this element, and then accordingly it has to do the operations on it. So that's why when we're using Python lists, it's very, very it's a lot of performance impact is done based on what is the type of that element and what is the size of the current size of this list, because it can grow dynamically. Now let's consider a simple example. I have got two 1D arrays of same length, and we want to multiply each of these elements with the other one. So suppose these two, the data is stored in two Python lists, A and B, and we want to iterate through all of them, multiply them, and store it into the third list. So this is a simple code here. So create a C as an empty list, and we iterate through, because the length is same for both A and B. So we iterate through each of the element, and then we multiply each of these element, and then store it into C. Now here, as we just discussed, that for when Python is iterating through it, because Python supports it can be of any data type. For each of the element it is going through, it has to check what's the data type. It will waste some time there, and it also has to check the size of it. Although we have provided this I in range, but still it has to interpret it, and every time it has to check the data type and then do the multiplication. So this will produce the correct answer, right? It will, because this is correct behavior. It will be able to give the correct answer in whatever we are trying to do. But what will happen if we have got millions of numbers? We have to pay the price for the inefficiencies of looping in Python. This looping part, right? Because looping through each element and then checking the data type and then do the multiplication and all, this has got performance impact. For the small areas, it would be fine, but if we are talking about the big data, millions of data, this will have a severe performance impact. It will be very, very slow. Now, if we try to write the same code in C, say, or for example, C programming language. So here, because C supports it doesn't support dynamic data type, it should always should be static data typing, which means that the compiler already knows what is the data type stored. Okay, just like Numpy. And once we multiply this, there would be no time to deduct what is the data type. It will all perform it at a very fast way. And because C, all the methods in C are very close to the machine programming language. That's why, performance-wise, C is always having very, very close performance as compared to Python or any other language. It will be very, very fast. Now, of course, we can use C for having a high performance multiplication here. So, but if you are using Python and all, we have to think about a different way, that if it gets the similar benefits of Python, it should be very concise and should be easy to code, and also it has got a performance as same as near to C. So that's where we are looking what it comes to create this Numpy module. In case of 2D arrays for C also, we can have two for loops, and then we can do the multiplication. It would be very performance-wise, it would be better. But for using Numpy, it gives us the best of the both worlds. element by element operations in the default mode, and it should be also like can give us a very high performance, same as this C code. In Numpy, we can simply write one line: C is equal to A into B. We don't have to use any for loop. We don't have to use any type of like using Python and all, where we are going through each of the elements using this for loop. Instead of that, we can just use Numpy C is equal to A into B. This simple, concise thing, it will give us near C speeds. I mean, whatever the performance optimization we're talking about using the C language, the similar type of performance would be achieved by just using this one line, and it will do the same thing. It will multiply each of the elements in A to the B and give the output in the C in the same dimensions. So it's like a 1D array of like say 5 elements each. The product C would be also of 5 elements, where each element is a multiplication of each of the ith element in A and B. Now this previous example, C is equal to into B, this illustrates like two of the most important Numpy features, which are the basis of much of its power. First is vectorization, and the second is broadcasting. Let's talk about vectorization. So here in this example is an example of vectorization, right? We are just doing just like a mathematical operation, multiply A multiply by B. It's already it's an array, but it will do its necessary stuff and show the output in C. So although I mean it's like very much straightforward, we are removing all those like loops that we have encountered before. Like in C, we are using this for loops and all. But here in Numpy, it's there is an absence of looping. We totally remove the looping part. We don't use any for loops and indexing, etc. For example, we are using indexing as well. For example, we are using I and J indices in C and Python as well, Sunshine Python. But for Numpy, we remove all this. We remove for loops. We remove indexing. Although behind the scenes, this is already happening. We are still having this for loops and everything in the pre-compiled C code, which is already optimized. So behind the scenes is still happening. But when we are writing the code using Numpy, we don't need to worry about it. And it will also give us the near C speeds, because it's actually at the background, it's still using the same C code and it's already pre-compiled and in an optimized format. So that's why vectorization is one of the coolest features of Numpy, which makes it very, very fast. And it's very easy to write, because as we can see that it's very much resembles to a very like a mathematical function, that how we multiply an array or a vector. And because we are using only like one line, and it's like more concise and easier to read, and it's a fewer line of code. Fewer lines of code means that it generally means fewer bugs, because if you have small amount of code, it's very easy to not fall into the bugs. And as mentioned, it resembles standard mathematical notation, just using multiplication. And it's very much like a Pythonic code. When you talk about Pythonic code, although it's like in Python standard lists, we are using much of the loops and everything to iterate through all the elements. But using Numpy, we remove all this inefficiency and difficult to read for loops, and use vectorization, which is very, very fast. And the second part is vectorization and broadcasting. Broadcasting is another feature which makes it very fast. For example, if we have got an implicit element by element behavior of operations. For example, if we have got say Numpy, and where we want to do a lot of like bitwise operations, functional operations, or calling some logical operations. In that case, instead of behaving any element by element, looping through it, we can use the broadcast message. I think it would be more evident when I show an example. So suppose we have an ND array containing 2 elements, 1 and 2, and we are multiplying it with a scalar 1.6. So instead of looping through it, right, instead of going through like each of the elements and multiplying it one by one, so there's a like using broadcasting. I mean, again, there is a pre-compiled C code which will make it look like that it's not looping through it index by index, but it is multiplying it. But at the back end, behind the scenes, it will be still multiplying each of these elements by 1.6, and then the resulting ND array would be 1.6 and 3.2 as given here. But when we are using this, this is actually giving an impression of the broadcasting, that because we are broadcasting this element. If the array is like say of 100 elements of like very, very large array, if you are just using multiplying it with a scalar value or adding it, it will be immediately applied to all of their elements without using any type of loop, without any using for loop by iterating through it, because everything which is behind the scenes, is all the pre-compiled C code, which is making it very, very fast. So that these are the two very important features for vectorization and broadcasting, which makes NumPy unique and very, very useful for other higher level scientific computations in which we are involving large amount of data, millions of data. So in the interviews, it's a very common question that why NumPy is very fast. So you can just highlight like two basic points, that NumPy arrays have a fixed size, which makes it very, very, very fast, as we discussed. And also it is of the same data type. That's why it's fast. And everything, all the operations on this on the ND arrays are actually performed in a pre-compiled C code. And the other feature is that it also supports vectorization and broadcasting. So these 2, 3, 4 features that we discussed, that is the fixed size, the same data type, at the background is a pre-compiled C code, and vectorization and broadcasting. These are the things that you can demonstrate and in the interview, because it's a very, very common interview question. One of the first questions, that why NumPy is very fast and what's the difference between a NumPy and a Python standard sequence. So you can highlight these points. So these are important points, and also to make it that why the NumPy is used as a basic package for learning data science.